Countdown, 5, 4, 3, 2, 1. And hello, everyone. I assume we're live. I assume we're live. I've still got this button which says session starts in 0. If we are live, if someone can just type something in the chat, that would be helpful. And someone who's watching this, great, fantastic. Great. We've been having some issues, I think, with this platform all week. But welcome to this last session on synthetic data and text analysis. We have 4 great speakers lined up, and I think by now you should all be familiar with the format of these talks. Feel free to drop any questions in the Q&A box while the speakers are talking. If they cover your question, you can always delete your Q&A before we get to it. I will leave some time after each person's talk for Q&A that's already in the box, but otherwise, write your questions at any time, and there will also be a Q&A session at the end. So without further ado, I will hand over to Johannes, and he's going to talk about his package Simpop.
Thank you very much. So good afternoon, everybody. My name is Johannes Gussenbauer, and I will talk a little bit about the Simpop package, which my colleagues and I modified a little bit, so we improved it. So this is a joint work with Matthias Tempel, Ciro Fritzmann, and Alexander Kovarik. I myself work at Statistics Austria as well as Alexander Kovarik does. So let's just dive in. My talk will be structured as follows. I will just give a quick intro into the Simpop package. It's actually already a couple of years on CRAN, and then talk a little bit what we improved on, what aspects of the package we improved on. So the Simpop package itself is used, or the purpose of it is to generate synthetic microdata. And when we talk about microdata, we mean household type data or census type data. So you have households with certain attributes and people living in these households with certain attributes. So this is the main focus of this package. Why should one use or generate synthetic microdata? I think it's quite obvious, the benefits. First of all, it's really needed for the scientific community. So maybe a census bureau has this kind of data, but not all the public. It's often not possible to disseminate this data. And if you can get your hands on such microdata, then this is usually highly censored, or it takes a long time. When you generate the synthetic data, you should obviously not reveal sensitive information and preserve this correlation structure between the variables that each individual or household has. And you can use it for prototype development or microsimulation, the synthetic data at hand. This is kind of the workflow of the Simpop package. You usually start at least here, or you have already a calibrated sample, or you maybe have the whole population and want to do a synthetic version of this. And then you define some household structures, and then you add in periodically more variables, be it at a personal level or a household level, using different kinds of models. And afterwards, you have this, we call it calibration step, where you can specify or improve the distribution of the synthetic data even more. And then you have the output, which is your synthetic population. So one of the improvements that we did was including the XGBoost package into the Simpop. So you can now call this XGBoost models when using the modeling steps to enrich the synthetic variables. There are obvious benefits for it. So one of them is that it's really strong out-of-the-box method, and you have great tuning parameters. You can also do cross-validation quite well. So it was an easy choice for us to include this, and now this has been done. And so for these routines that are available, which basically do the top does basically add a categorical variable to your synthetic data set, and the second one adds a continuous variable to your synthetic data set. And what you do here is basically just specify the XGBoost package, and then you have this regression model which tells you what kind of model you want to have, and then it will apply it on the synthetic data. You have these model parameters which can override the defaults of the XGBoost call, which is underlying basically. So this really is just an easy enhancement to these routines which already exist. Here's just a comparison, just to give you a quick insight on what the benefits are. There are other methods already available, like the multinomial model or a random forest or a decision tree model. And Ciro Fritzmann and Matthias Tempel looked at an EOSilk data set. So they looked at this kind of census-like data set and figured out that for categorical variables, at least, the XGBoost performed better than the existing already implemented methods. So this is an actual improvement to the functionality of this package. And there's just one correlation structure here. Basically, the darker the colors, the more you deviate from what you would expect. And the lighter the colors, which you see here on the right side, means that the XGBoost is capable of reproducing the distribution in the synthetic data better than the multinomial model. Yes, and now for the calibration of the synthetic population. This is a bit of a, I think, SimPop specific feature. So we say we want to calibrate the synthetic population to basically fit a selected distribution. And usually this is not really straightforward. I was saying that we have households and people living in households. And usually you then, after you have produced your synthetic population, you might want to improve the distribution, so the age distribution, or on a lower geographical area where you want to get certain economic variables, the distribution of them correctly, like education, or maybe something like income brackets or something like this. And then if you can't do this well with the modeling, then you can use this calibration to improve this distribution for your final output. Or it could be that like the starting sample or the starting population that you have doesn't cover this variable very well, and you have kind of like census tables which you can rely on, which have the official or the more correct distribution, which you can then fit your synthetic population onto. So we use a simulating annealing approach to try to get an optimal combination of households and people which try to fit this target distribution. And the difficulty here is basically that you have to take complete households with people living in there, and you cannot pick the people apart. And this makes it quite a difficult problem, actually. So that's why we're using the simulated annealing approach. And just to give a quick overview on how this works, you start with your synthetic population, you multiply it by a factor, you make an initial selection of households, and then you have this objective function. So you then compare the distribution of this selection with the target distribution, and using some kind of objective function, which I'll talk later about what we did there, to see how well this fits. And then you change households, basically. You redraw some and you discard some, and then you check again and try to accept or reject a new solution until you kind of get as close as you specify. So I say this differ by an epsilon, so you can specify kind of like an epsilon, and this is how close you want to get to this target distribution. And what we improved here is that we now allow for multiple different distributions. So prior, you could also only give a joint table. And now you can give many different tables, which can be on an individual or an household level. And this also meant that we had to advance the objective function. Also, how do you redraw your individuals? How do you do this smart? Because you do this by sampling with probability and not just completely random. So you have a chance of terminating actually the algorithm. So these are our main changes now for this calibration. We have this objective function, which is just squared arrows. These n and tilde are basically my target distribution, my distribution currently, and the other one is the target distribution, and these n's are basically the cells so the number of people or number of households basically. So I take something like a squared arrow here, and then for the sampling probability, when I want to redraw a person, basically the idea is if I am missing kind of like this person in my target distribution, if I'm missing people who are age older than 60 or something, then I want to sample them with a higher probability. And if I have too many of a certain demographic, then I want to sample them with a very, very low probability. And in the discarding step, I want to get rid of them basically. And so this is what we did here. We have this F, which is just kind of like a term which should tell us kind of like how much do I need this person basically. And if I do need it, then I try to sample this. If this is a negative and I do not need this person because I have too many of, so to say, 60-year-olds or something like this, then they get a really small sampling probability. So this P is a sampling probability. And for the discarding step, this kind of flips around. So if I have too many of them, then I will discard them with a high probability. So this is kind of what we did. For the P equals 1 case where you have just one table, this just defaults to this difference basically. So all these sums will just collapse to just this difference basically, which makes intuitive sense. So if this is positive, then I have too many of them, and if this is negative, then I have too few. Yes, so this is one major improvement that we did. And another thing that we did was we improved the programming behind this to make it a bit more efficient. And basically, this is using the toy data that is done, that is supplied in this SimPop package itself. So we have here the magnitude of the population size and the number of seconds it takes to calibrate this. And before it, we were more in the magnitudes of minutes and hours for this exercise. So now this is kind of like just to give you an example on how far we tried to improve on just basically the implementation of it. It's not all done in super fast C++ or something, but it's just trying to write the more efficient code basically. So yeah, I think I kind of I'm good in time. I think here's just some references. Happy to answer any questions now or later, and thank you for listening.
Thank you, Johannes. That was an excellent talk and one of the few presentations where the presenters actually attempted to go through the mathematics. So really well done there, Johannes.
Thank you.
Oh, we do have a question pop up. Let me read this. Right, so this is from Janeth. Does the SimPop package use a custom implementation of simulated annealing?
Yes, so this is what me and Alexander Kovarik basically did. This is so we don't rely on any other packages. It is just the simulated annealing as is not a difficult algorithm. There are some like specific things that we implemented, which we figured out when applying it to real world problems. Basically, something can happen where you draw a lot of large households and you cannot get rid of large households, and then your population gets bigger and bigger and stuff like this. So there are some kind of very specific correction features there, which try to get you on the right track for this purpose of getting this synthetic census data, basically. So yes, this is our own implementation, basically.
Great. Well, actually, I have a question of my own that sort of came to mind when you were doing your talk. You mentioned that you recently added XGBoost as a feature of the package. I just wanted to maybe get some more background on sort of how that came about. Was it through sort of your own needs that you needed to add this? And my second sort of part to that was, and I was attending our core panel session earlier, where I think Martin was how at the time when he developed some of his packages, so like the cluster package that was sort of state of the art 20 years ago, and now it's sort of become less relevant. Do you see sort of is XGBoost sort of as far as things are likely to go, sort of in sort of the future you see for your package? Do you see adding further functionality?
The first one was why we implemented the XGBoost, or
Yeah,
what motivated us. So this was done by Matthias Tempel and Ciro Fritzmann, and Ciro Fritzmann is a student of his, and he did it for his master thesis, basically. So implemented the package and did some tests, and what they found was that for instance with the categorical variables, the XGBoost performed very well. We also have the random forest ranger model available to use with the package. So for categorical variables, this went well. For numeric variables, and this was using this EOSilk data. So this is on income and living statistics, and there's some income variables there, which is always very difficult to model. Income is not easy to do. The current like functionality that exists in SimPop yielded a little better results than the XGBoost. So it didn't like outperform on every level.
Right.
What we try, or what we want to actually do with this SimPop is that you would want to automate this synthetic data process as well as possible. And if you could have a good out of the box method, then this is always good, because you can always write you can always do your variable transformation in such a way that at the end of the day you just need a linear regression, and then you're done, if you know how to manipulate the data well enough, I think. So if you really do this for a case, then it would take a lot of time. And I think this methods, also the random forest, they just take the step away from you, and you don't have to invest so much time for this little this little things, or this little tuning things, so that this is not so burdensome. I mean, you do have to check the outputs and everything, and there's still a lot of improvements to be done. The SimPop as it is right now does not really, or it's a bit difficult to model the household structure as it is. So you cannot really, you have to rely a little bit on the sample or on the data that you put in there, and there are with this household data, there are a lot of pitfalls that you can come up with. So if you would just really go from if you wouldn't rely too much on the sample like it is at now at this SimPop, so you do have this household structure where you basically specify what is the age structure in each household, and you rely very heavily on the sample data that you have there. If you wouldn't do this, then you would get into real troubles because you can't have households with only children, or you have data where you have the marital status there and you cannot be married. There cannot be a marriage between two children, or you cannot be married between an adult or a children. If you are not careful there, then your model will have it, and there will be pitfalls. And something else that came up was that when your data is really large, your population data, so we did a work where we had where our population was over 100 million people. And then if you have a model which predicts for each individual, has this probability vector, what kind of education a person has, then some of the models or models sometimes don't have zero probability or one. So there can be, you can have like infants or children, and they have a one probability that they don't have any education because it's not possible that they have any other education. But your model may say, well, it's not really one, it's 0.999999, and the others also get a really small probability. And if your sample is, if your population is large enough, then you still get like 10 people there, which you have to check manually then again, and then have to like manually say this is correct.
Yeah.
So this is a difficult. There's way for improvement, but it's difficult.
Right. So there's a future pipeline for your package still waiting to be improved. Great, thank you, Johannes. So our next speaker is Emil Wiedfeld, and we're talking about text recipes, which I believe forms part of the tidy models framework. So over to you.
All right, thank you so much. Yes, that's correct. It is a small sliver of what encompasses the tidy models. And I'll be talking more specifically about test recipes today and what you can now achieve with the package to do your test pre-processing. So typically you have some data come in, and it might have some test variables included in it. And those test variables generally won't be immediately useful in the model, since it's a bunch of tests and it tends to be unique. And as in this case, you can have quite a lot of text. So even a dummy encoding wouldn't work. So we need to somehow transform this data into a numeric format that can be used by our different machine learning models. So ideally, we want something like this, something with numbers in one way or another that will readily be accepted by our model. And what you find is that the steps you need to take to get from this very unstructured text data into the numeric data have the same structure 90% of the time at least, where we first want to take our text into tokens, which is a smaller unit of text. So it could be words, it could be letters, it could be sentences even, just any breaking the text into a smaller size. Then we might want to modify those tokens in one way or another. It could be lowercasing, it could be removing ones we didn't want, or focusing on other ones we really want or combining them in different ways. And lastly, we need to count these tokens in a way so it would simply be just counting the occurrence of each of them, but we can also do it even more like fancy things. But at the end of the day, it's all about counting how these tokens appear. And this is where test recipes comes into it. So it integrates really well with the recipes package, which gives a lot of benefits by having a lot of the underlying framework taken care of. It also means that you can readily use test data alongside non-test data. So you can have a normal recipe that handles all your other variables, and then you use test recipe specifically in your code to modify the specific test variables. It also has this like modular framework that comes from recipes. So every action you do to your test variables are isolated, and there's a high degree of like specificity, and from that comes a lot of flexibility, which I will show in the following slides how we can utilize that to really specify what you want. And I find this to be one of, if not the most flexible pre-processing engines out there. So first, we want to start with tokenization, which is the act of taking our text and turning it into these smaller units. So here I'm just doing a small example using the animals data set I have, which is descriptions of different zoo animals. So we're loading in recipes and we're loading in test recipes, and we specify the recipe to say use the test variable and divided data, and then we are saying using step tokenize, which once this runs all the way through, it will take the original text we have and turn it into a list of tokens. Here it defaults to word tokens using the tokenizers package to find out what's a word. But the extensibility is we can change how the tokenization is happening. So we could say, oh, give me all the character tokens. And any tokenizer from the tokenizers package is available. You can pass in options to change how everything is happening. What is new in the latest version is the addition of first order support of these different tokenization schemes. So now we have a first order support of like byte pair encoding from the tokenizers BPE function or package. And it works in the set, and I'm not going to explain today what a byte pair encoding is, but this type of tokenization is a trained tokenization. So it takes some data and it learns how to split the text into smaller units. And the test recipes framework allows us to train how this tokenizer needs to perform on the training data set, and then reapply the same tokenization once we apply it on the testing data set, instead of trying to retrain how to do it on the testing data set, because we would lead to various bias and other things. So we have a trained tokenization here. We also have support for sentence piece, where it's a lot of the same ways as byte pair encoding, but might be a little bit more sophisticated in some ways. And lastly, we also have a full support for the word piece tokenizers. Then another tokenizer that then works a little bit different than the other ones, but we have full support for both these untrained tokenizers that just statically does the same thing every time, or these trained tokenizer that learns how to tokenize something depending on the test. And sadly, with most things that with us test, there's no free lunch, as in there's no one best tokenizer. You need to look at what your data says, how to extract information. It then also depends a lot on the type of data you're coming in. So tweet data, which is very popular, will need to be analyzed and modified in a very different way than these long paragraphs, because for tweets, very short, we can't afford to throw away too much information. Once we have our tokens, we can use these tokens almost immediately, but we might want to do some small modifications in it. So one thing we can do is we want to stem them. So stemming, in a very general sense, is removing the end of words according to some algorithm. So step stem defaults to the snowball algorithm, which is a language-specific stemmer, which then can be controlled using arguments. And as you can see right here, classification, I think the classification is now classif, and all these different words have part of a ending remove. This might be useful for you if you want to, if you feel, I like to think of this as you have a bunch of different buckets where each different unique word corresponds to a bucket, and stemming collapses multiple buckets there, because you might have family, families as two different words, but you want to count them as one because there's not a noticeable difference between them. Stemming might be able to work in this favor. Stemming is also very fast, but then no free lunch, nothing is superior to something else. We can also use step stop words to remove stop words, which is words we think that might not be useful. Then this is a very, I find, controversial task, because what is a useful word is nowhere near defined, but you can pass in any list of words to this step and it will remove them. Likewise, you can use this step opposite and say you want to keep it. So if you know exactly what words you want to count in your text, you can pass it as a stop word list and just say, I want to keep all these words instead. One new thing we added fairly recently was the ability to calculate engrams of our tokens separately from the tokenization step. So as you can see here in the first one, you can see here, instead of having each token be one word, it is a rolling sequence of words, here defaulting to 3. So the first token will be the first, second and third word combined. The second token is the second, third, and fourth token combined, and so on. So we might be able to count some more structural patterns in this. Where this really excites me is by separating the way we generate these engrams from the tokenizer allows us to do things in between. So here we are seeing, first we start by tokenizing, then we calculate the stems, and then we engram on the stems. Something that can be very hard to do in other frameworks, because calculating engrams a lot of times tends to be part of the tokenization step. Lastly, one problem you might run into is the text inherently is messy and annoying to deal with. And you might have some tests of a name we have shown right here, and they look the same, but if we try to compare them, they're not the same. The reason why they're not the same is because the first one, the unit character, is a circle with the umlaut, the 2 dots above it, where the second word is an O followed by the 2 dots above it, and they print similarly, but they are different. For a computer, the computer doesn't know any different. These are different characters. We have a step called step text normalization, uses the stringy package that has algorithms to deal with these types of issues. So if you have text that's like slightly different in these specific types of way, sometimes it can be normalized to say always keep like these accents as a separate character than what they're accenting all at otherwise, and then these characters would be the same afterwards. This is just some of the different steps we have. There's many more available. We're also always open for more types of calculations come in. I'm personally thinking a lot about how to have proper emoji support for all of this. So if you have any thoughts about it, contact me any way possible, and we can see if we can figure this out. Lastly, we come at the very end, we generated our tokens, we modified them in ways we felt was important, and now we want to turn this into numbers. So here we have and there's then many ways of doing it. Probably the simplest way is counting how often different tokens appear. So here, ending with step TF, short for term frequency, and it will count how often each different words appear in our corpus. For each word, it will also know which words are being counted. So once we reapply this to new data and it sees new words it doesn't know, it's not going to count those words, but it knows, oh, I'm counting these 100 words. So new words won't mess up the output. You always get the same output format every time. You can also do like more fancy things like TF-IDF, which is a weighting scheme. The weights, we have both how often words appear across observations and across corpus wide. And there's some weights that are needed to calculate these transformations. Those are stored in the recipe to allow you to perform the same calculations equally later. So you have no data leakage coming in. You should always have the right calculations from end to end. And lastly, one thing I want to mention we have as well is text hashing, which, long story short, takes a hash of a token using a simple cryptographic function that is a number between here 1 and 256, and maps each word to one of those, counts those up. Here it has a double function that also does a plus minus to avoid some collisions. But then many more, we're slowly adding more and more. We also have support for word embeddings and so on. And that is all I have. There's links to test recipes that both Julia, Silvia, and I wrote using this package to do supervised test analysis using tidy models and Terrace. A blog post where I have some examples, and you can tag me on Twitter anytime. That's all. Thank you.
Fantastic. Thank you, Emil. That was very well organized and well laid out talk, I thought. And
thank you.
Hats off to everyone who actually understands all these text encodings as well.
It's not a fun job to do it. Like hopefully, this is all post encoding issues.
Great. We have one question, which is we're running a bit behind time, so maybe if we try and keep the answer short. But question from Robin: why would you hash a token? Seems quite a genuine question.
Yeah. So the reason why this sometimes works well is by trading these hashes, you have, first of all, it's very fast calculation, and you have a deterministic transformation from any word into a number. And depending on how many words you have, you won't necessarily have that many overlap, but it allows you to have map any size corpus into a fixed width. So if you know, oh, I want 100 predictors out of this, using hashing, you can guarantee to always get 100 predictors, no matter what input you're getting. And then you might run into issues if multiple words map to the same hash, because then you won't be able to tell what word contributed, like which direction they contribute once you fit the model. That's the main downside, is you're losing some interpretability from this. But it's mainly used as a speed and consistency method. But you don't need to make a decision of only keep the most 100 or most 1,000 most common tokens. You can use all of them.
Great, thank you. So let's go straight to our next presenter, who is Janeth Wanyarachi, talking about the scatter package. Over to you.
Okay. Thank you, Charlie. Let me share my screen. Yes, I believe everyone can see my screen. Yep. All right. So I'm Janeth Wanyarachi, and I am a student of University of Sri Jayawardhanepura, Sri Lanka, and I'm studying for my bachelor's in statistics. And I'm going to be presenting to you today Scatter, which is a package that can generate instance spaces based on scagnostics. Now, the word scagnostics might be familiar to some of you who were there for the data visualization session yesterday, but even if you weren't, I'll give a small catch up on what scagnostics are. So basically, scagnostics are a group of measures that evaluate scatter plots, and the late Leyland Wilkinson developed the graph theory-based scagnostics to quantify the features of a scatter plot into measurements ranging from 0 to 1. So here you might see that the clumpy value, when the clumpy value is really high, the scatter plots tend to be clumped together. Now, for example, if you take this scatter plot, it'll have a set of, for n number of x and y data points, we'll be having a 9x1 vector of scagnostic values. And here you can see that the skewed value is a bit high, and the rest of values are similarly leveled as well. Now, how does scagnostic work actually? What they do is they normalize the data into a unit interval, and for computation efficiency, we bin the data into hexagon grids. And after that, we define a minimum spanning tree. So a minimum spanning tree is a geometric graph that connects all of the points to each other using edges that have the minimum distance among them. And also, it makes sure that there are no cycles within the graph. And once we define this MST, we can remove the outliers based on this MST. And we define a new MST on the outlier removed data set and an alpha shape. So an alpha shape is kind of like a border around the scatter plot. And we also define a convex hull, which is like a boundary around the scatter plot. And based on the features of these three geometric graphs, which are subsets of the linear triangulations, we calculate the diagnostic measurements. So how did I end up here? Now, as part of my research, I needed a way to give marks for different features of bivariate dataset. And that is exactly where diagnostics came into play. And as the next step, what I want to do was I want to generate bivariate datasets which would have the diagnostic values that I expect. So basically, an inverse diagnostics. And I looked into whether there were existing solutions to this, and surprisingly, there aren't any. And that is where I found my sweet research gap. And from there onwards, I thought of how I can generate data from these diagnostic values. Earlier, when we were given an n number of xy coordinate pairs, we got a 9x1 vector of diagnostic values. Now, when we are given a 9x1 vector of diagnostic values, we need to get an n number of x and y data points. So we have to reverse a function, right? So it sounds pretty simple. If fx equals 4 plus 3, the inverse function could be written like this. Now, how are the diagnostic values calculated? Well, they're calculated based on different features of the 3 different geometric graphs. So some of them will be using the length, some of them will be using the area, and even some might be based on simple correlation. So you can see that these equations are exactly one-to-one functions. And here, there might be even multiple data sets that might satisfy all 9 of a given specified diagnostic value. So this started getting a bit out of hand because I would be generating a set of data set, and when the data set is generated, the geometric graphs that are defined on top of those data points will need to have the features that correspond to the exact diagnostic value that is there calculated through the functions. Now, I was thinking about this quite a lot, and I was pretty bummed out about it. So I decided to go ahead and have some ice cream. And when I'm having ice cream, I tend to put some sprinkles on top. And it was at this moment that I had my eureka moment. And the idea was, why don't I first sprinkle a little bit of data points on a 2D plot so that they land in the right places, and on top of that, I add another set of sprinkles so that they are also landing in the right places. And I keep on doing that so that the final set of sprinkles looks actually really good. Now, this at the very beginning might sound a bit like Archimedes screaming Eureka and running around naked, but once I formulated the idea, what I wanted to find out was how I can arrange these points in the most optimal manner. And to do that, what I needed to think of was, I needed to define a loss function such that when given an n number of x and y data points and 9x1 vector of expected diagnostic values, I needed to quantify the distance between this calculated diagnostic vector and the expected diagnostic measurement. So there I defined the loss function based like this. Basically, what happens here is I have a 9x1 vector of calculated diagnostics and 9x1 vector of expected diagnostics. I'm taking the mean average error between these two diagnostic vectors to get a final loss value. Now, I have the loss function defined. Now, all I need is to find an optimizer for the 2n parameters of x1 to xn and y1 to yn. So for any n number of data points, I'll be having x and y coordinates. So I'll have 2n parameters. Now, the algorithm that I selected was the same as what Johan has also selected, simulated annealing. So simulated annealing, the name comes from material sciences, where we heat something up really into a real high temperature, and then we cool it off to change the properties of the material within itself. And the algorithm works similarly, where we have a high temperature, and in that high temperature, the algorithm tends to select worse solutions and then try to explore the solution space. And as the temperature decreases, the algorithm becomes greedier in selecting the most optimal solution. Now, with this optimizer in hand, I was able to build the algorithm that you can see here. So at first, I would be checking if I have reached the number of iterations, and if not, I would go through and check if this is the first time that I'm going through this process. So if so, I would select the initial data points for the optimization algorithm based on random values from uniform distribution. Now, once I get the optimized data points, I save those into a separate vector, And then in the second round, I use the obtained data points and add a small error so that they add a small error and pass it on to the simulated annealing algorithm, so that the algorithm will be searching in the local neighborhood of the previously obtained optimized data points. And likewise, I'm adding on top of these data points to get the final set of data points that will have an overall minimum distance between the calculated and the expected skagnostic values. And all of this is packaged in the scatter package. So you can install and try it out yourself from this link here as well. And afterwards, you can simply use it. Once you install it, you can simply use it by calling scatter and mentioning this measurement that you want. So you don't have to mention all of the skagnostics like monotonic this much, clump this much, and so on and so forth. You can even mention a small number of points that you want to mention, a small number of measurement types you want to mention, and then you can mention the number of points you want. And here I have set the error variance to 9 to get a bit more spread around the values. And once you've done that, you can visualize it, because this straight away gives out a table with X and Y values. And using qplot, you can simply visualize it. Now, what happens actually behind the scenes is, for each epoch, simulated annealing will start looking into the best position that will minimize the loss that you can see on the right here. And once it does find that position, so now it will those points are colored in blue, and the blue points on top of the red points are considered when calculating the loss. And likewise, so it will try to find the best positions that are available with the current fixed data set and the variable data points as well. Likewise, this will go on for another epoch. So I have only shown here the first 200 iterations, but it actually went in for a longer period. And simulated annealing is done through the GenSA package in my case, and that is how the entire scatter algorithm works. Now, the scatter function also has a comprehensive documentation on how to use it. You can check the arguments, which will be a number of points, the initial points. So the initial points are the initial number of sprinkles that you sprinkle on top of the data points. That you can increase that number or you can decrease that number, and we can see how that affects the performance later on. Now, speaking of performance, if we look at how well scatter is doing, so I did an experiment by generating 50 points for 20 times using 5 initial points, and I set the expected measurement value from 0 and to 0.5 to 1.0 for all of the 9 measurements. And what I found out was it's easy to get a skagnostic value that is quite close towards 0 and 0.5, but getting a perfect one is a bit difficult. And you can see here in sparse also there's an issue of having a high value. So we are working currently on top of how to fix this as well. And earlier I mentioned that there's the hyperparameter of initial points. So when we increase the number of initial points, what would happen usually is that the number of seconds that it takes to generate the data set increases, but there are some specific cases where the change doesn't actually happen that way. But in most cases, trying to get a perfect one with high number of initial points ends up with a lot larger number of time taken in seconds. But overall, scatter is able to generate 10 replicates of 50 points with a mean time taken for all of it with under 20 seconds. So the highest is for the outlying one with 19.8. And in all of these cases, you can see that getting a perfect one takes a bit longer time than usual. In some cases, getting a 0 also can be quite difficult and stringy and skinny. So overall, scatter is able to get these values pretty quickly. Now, what exactly can scatter do for you? So this is how scatter works. Now, what can it do for you? Well, if you are a teacher, and in the audience, if you are a teacher, you can generate generate dummy data for students to try out new statistical methods through this, or you can use this to introduce students to the concept of skagnostics, and thereby introduce them a bit more into data visualization and exploratory data analysis as well. And if you're a data scientist, you can synthesize small-scale numerical data sets for test purposes, and also you can generate dummy data to try out new data science methods that you find. And if you're none of the above, and if you are just an everyday R user, you might have experienced a lot of packages throughout this conference by now. And if you want to generate a quick sample of data to test out a new package that you installed, you can simply use this to generate a set of data to try it out. And also, you can also use this to generate data for any interesting generative art that you have in mind. So for example, this was created basically using the Palmer Penguins dataset, and this showcases the bivariate numerical relationships that were generated through scatter and using polar coordinates and some stat smooth geoms as well. Right, so where to from here? Well, mainly what we want to do focus on was, so yesterday in the data visualization session, Harriet Mason introduced two or three more skagnostic measurements as well. So we will be working on building those and adapting those into our package as well. And we'll be looking into better optimization methods, writing custom simulated annealing methods, and even parallelized implementations using the Futureverse. And currently the GenSA package and the skagnostics both are working with C++ behind the scenes, but intermediate computation is done through R, so we might want to bring in that as well. And there'll be many more updates as well, so stay tuned. And with that, I come to the end of my talk, and I have to give two shout outs. Thank you so much to my supervisor as well, Dr. Tianga Talakala. You can check out her work on GitHub. And also thank you to USAR 2022 and the sponsors of USAR for awarding me with the diversity scholarship that gave me the financial strength to speak before you, because right now our country is going through a tough economic crisis, and the diversity scholarship really helped me get the financial strength to do what I am doing right now. And if you have any follow-up questions, you can email me, send me a DM, or follow me on GitHub or LinkedIn. And I'll also try out Scatter, and the slides will be available at this link. I'll send it off as well. Thank you.
Thank you. Very entertaining. You did a great job, Janet. Very good. So my question from me, my first one to you would be, when are we going to see the package on CRAN?
It's still under development. I'm doing some experimentations on the versus time distance to see if I can actually make a function that can synthesize an entire data set. So that is still under work. Once that is settled, I will definitely be pushing it into CRAN.
Great. Well,
in the meantime, I'll drop the slides into the chat as well. All right.
That will be great.
Thank you.
Okay. No more questions at the moment. So Olivier will be talking about sentiment analysis. So over to you.
Hello, everyone. So if you can see, I'm going to present, well, I have to be fast because we don't have much time left. I'm just going to set a timer. So I'm going to speak about my package Centopic that I uploaded on CRAN recently. So it's an air package that aims to join sentiment and topic analysis of textual data in order to derive, for example, indices over time that take into account sentiment and topic content. So just, yes, you know, there's like more and more textual data available on the web. This is especially true for newspaper, public statements that are transcribed and hosted online. For example, here we're going to be interested by the ECB. So yeah, this is just an example of how textual data from news is sometimes used to help forecasting macroeconomic quantities. So this is the Economy Policy Uncertainty Index that basically monitors how much attention there is to news that speaks about uncertainty over economic policy. So this is the one developed for Belgium, and it spiked whenever there's like some really uncertainty, and it has been used in a lot of application to forecast macroeconomic quantities. So this is, I think this kind of objective that might help to do with this kind of analysis. Just to give it a bit of context, now a hot topic is the inflation. Everyone is wondering what is going to be able to happen to the interest rates from the ECB in reaction to the huge increase in inflation. So yeah, you could try to forecast a bit the decision of the ECB as a response of the inflation, but you will perhaps improve this assessment as well by using textual data. For example, the press statement that you have. So that's a bit the example I'm going to show today to use this methodology that is implemented in Centopics. So yeah, today the focus is to create topic sentiment time series, and that a bit follow the idea of whenever you create a text, a dissertation, usually you have sequence of IDs, paragraph, and each of them, they have a specific ID, and this ID can be presented positively or negatively. You can start a text by speaking about something and be really negative at the end, and then you can do another argument and speak about something else and be more positive. So when a text can display multiple different positions, sentiment. So it comes a bit from this. How do we extract this information? How do we recover a bit the thought process of the author when he was writing his text to have his specific opinion on different topics? So there we're going to leverage on sentiment analysis and topic modeling, and that's what you're doing in this package. So yeah, just about the data that you're going to use today is the ECB press conference statements that are released every month, basically, and that inform on the decision that ECB makes about its monetary policy strategy, as well as the future things that they can do, and as well as some economic outlook on the current state of the economy. Just to go back to what you're talking about. So in terms of sentiment analysis, usually there's a really easy approach that you can do. Is a dictionary-based sentiment analysis in which you consider that words are either positive, neutral, or negative. And how do you know whether the word is positive, neutral, or negative? Use the lexicon, which is, in other words, a predefined set of words that are explicitly categorized as positive or negative. For example, in finance, we use often the Logan-Maxent lexicon, which is used to analyze financial textual data. And you can see below list of words, for example, abundant will be classified as negative, and abundance will be classified as positive. And which is nice with this method is that you don't need to train actually. You consider that this is what I mean. This lexicon is a gold standard that you can just apply to a text that is somewhat in the same team. So that's what you're doing here. So as an example, this is, for example, decreased plotted in decreased frequency, the positive and negative words that you can find in the ECB press conferences according to the Logan-Maxent lexicon. So for example, here the positive words you can expect are strong, stability, positive, improvements, whereas the negative one you can expect weak, late, imbalance, decline, volatility. So this kind of words. Besides that, topic modeling. So this is really complex to explain, so I'm going to go fast over it. And hopefully, if you have prior knowledge, that's better. Basically, the main idea of topic modeling is to start from documents that you can on left. So just a list of documents that contain words, and you're going to fit a topic model algorithm on those, which will give you two quantities. So first, you have the topics, which you can consider as clusters of words that are related because they appear frequently together. For example, you will have one topic about basketball and another topic that will be about inflation. I mean, just random example. And you have a lot of words that are closely related to this. For example, for basketball, you will have ball, match, goal, and so on. Inflation, you will have very different words. And so you have those clusters, family of words that are created. And then you have, for every document, some kind of proportions that you estimate that tells you in these documents how much this document speaks about basketball or how much this document speaks about inflation. So in some sense, this is a way to summarize a corpus of text in an unsupervised way and to explain the main thematics from this corpus without reading any of the text. And then just you could use this summarization to find the most relevant text to a given topic, or just to understand what does the text speak about. Another way to see this is to consider some kind of factorization, where you have this document word matrix that looks a bit like what Emil presented before, and you try to decompose this into two other matrices, where on topics is a new dimension that appears, and basically cluster words together and a bit clusters document as well. I mean, I try to highlight how much those topics appears in each document. But maybe an example is better. So this is what the results of a topic model can look when you apply it on the ECB press conference. I just want to note that what you can see in the middle is actually something that I labeled by myself. The topic model does not label the topic, but I did. I looked at the words that were in each of those topics. So for example, the first topic I'm going to show you is the topic about inflation policy. So in these topics, you can see lots of words. You can see price, inflation, price stability, development. So myself, I said, okay, this topic speaks about inflation policy, so I'm going to label it as such. So here, what is interesting, you can see that the corpus, the entire corpus of text was structured in those different different teams. Notably, one that is interesting would be the monetary policies analysis and strategy. So it's a topic that's more focused on decision of the ECB. ECB, for example, relates to the interest rates. So this is an interesting one, especially for further away in the analysis. So what else you can have from topic modeling? You can highlight the paragraph. So in this case, the analysis is realized on a paragraph level. So you can highlight the most relevant paragraph for each of those topics. So that's the kind of thing that you can extract. As well, you can look how the attention to each of those topics evolve over time. So by using topic modeling, for every day, every paragraph published, you have those proportions. And if you know as well the date of the document, you can see how they evolve over time by just taking the mean over a given sampling period of time. And here, for example, you can see that at the beginning of the ECB in the year 2000, the topic Eurozone reform was really high because a lot of new regulation were implemented. Whereas uncertainty grew a lot in the 2009 due to the financial crisis. So that's the kind of thing that you can explore to see that attention over some topics can evolve over time. Now I'm going to speak about the topic sentiment methodology, and I'm going to be fast, so sorry if it is complicated. But basically, the idea is that you have, using sentiment analysis and topic modeling, you have some information at the document level. You have one scalar value that tells you the sentiment orientation of a text, and then you have a set of a vector of topic proportion. And we want to use all those two to derive something that is called the topical sentiment attention at any point in time, which is basically the sentiment effectively conveyed by a given topic in a period. So this is not just the general sentiment of your corpus, but this is the sentiment of your corpus that is relevant to this specific topic. So to do that, we're going to use those two variables that you have defined before. I mean, the sentiment analysis for each document, which will be STI, the topical proportion that you have for each document. You're going to use them and use them to make a specific time series aggregation. So we need to make two assumptions. That's basically what is annoying is like, remember what I said before, we have one thought process where you speak, you say multiple, I mean, you prepare multiple paragraphs with different IDs, and you have specific IDs regarding the theme that you want to discuss. This will be STI key, the sentiment in a document, the sentiment related to a given topic. But this is something that you cannot observe in practice because it's really required to estimate at the same moment with the same single technique, something that allows you to know the author's position on a given topic. So what you have is you have topic proportion that you know from topic modeling and the overall sentiment of the text that you can have with sentiment analysis. So one assumption that we make easily is that we say that STI would be equal to STI key. So that the sentiment is constant over the text. So we need to make this assumption, and it makes sense for short text because when you have short text, the more likely is that a single ID is represented. But there's a trade-off there because if you have less text in a short text, the accuracy of topic modeling and sentiment detection is less good. So I'm just jumping over it. So yeah, basically you have a trade-off of what dimension you should apply topic modeling and sentiment analysis. Here I chose the paragraph of that because I think that's the best dimension at which a a single ID is communicated at this level. So quickly about the aggregation. So we compute this quantity CTI key as the product of the sentiment of the author's opinion on a topic and the attention given to this topic. And so that's this product of those two is the topical sentiment attention. So that's the quantity that represents the effective sentiment conveyed by a topic in a given document. So you can aggregate this to make a time series. And I think what's interesting is that actually this on time series level, this quantity CTK is actually a decomposition then of the overall sentiment on the period. So it helps to decompose the sentiment that you measure with sentiment analysis into proportion that are determined by the topic modeling. So you can try to see how each topics contributes to your to your sentiment. So here I'm just going to show you an application of this on the ECB's decision, try to forecasting ECB's decision. So I use a field-specific lexicon that was developed by Pico and Renault, and basically tries to develop two lexicons, one that detects whether the monetary persistence is restrictive or accommodative, or whether the economic condition outlook is positive or negative. So this is just like lexicon I'm going to use there. That you can have some time series there. And for example, what's interesting there, you can see that the monetary policy went from accommodative went to restrictive to accommodative as the interest rate dropped during the years in Europe. So we have this topic model as well. And then we're going to use those two information at the document level to create this decomposition that you can see here, for example, in a smoothed way. So here's the actual sentiment that you have. Yeah, sorry for the levels. So you have this in black line. You have the overall sentiment over time that you measure with the economic condition lexicon, and then you have this breakdown that measure on average as deviation of the mean how the different topics contribute positively or negatively at a given in a given point in time. So can we use this to improve forecasting application? That's what we're going to see now. We have a quick application that forecasts ECB's decision. So we just define a target variable, which is +1 if the ECB decides to raise the interest rate or lower the monthly target of asset purchase program, and -1 if they do the opposite, 0 if it's neutral. And then we are going to use an ordinal probit model to predict this using two lexicons of Pico and Renault, and a set of macroeconomic variable, so the Eurozone HESIP, the industrial production, the 12-month inflation expectation. And additionally, what we're going to do, we're going to test whether we can improve this model with some information, with some topic-specific sentiments. So we're going to use EC and MP, and we're also going to add the difference between the economic condition sentiment and the economic condition sentiment specific to the topic monetary policy strategy to see whether we can isolate another signal from this. So that's the result of this aggregation for nowcasting the decision of the ECB and one period ahead prediction. And what is interesting there is that, of course, the sentiment, the sentiment analysis improves the forecasting ability of the ECB's decision. But further, if you also use this difference between the economic sentiment related to this monetary policy analysis strategy topic, then we get another significant coefficient, and we further improve the forecasting. So it shows that we can maybe better isolate the economic condition sentiment by using this topic modeling approach. So this is an encouraging results. I'm slightly over time. So here it shows that there's some clear value in analyzing the textual data published by the ECB, and that you can also use topic modeling and sentiment analysis together to try to create something that is cleaner than just raw sentiment analysis. But there's some limitation there because the topic modeling is in sample. So topical weighting about future information. That's something I have to fix. And then the decision variable could be improved because the interest rate is locked to 0. So recent year is a bit more complicated. So all of this analysis can be replicated using the Syntopics package that is on cron. Basically, that implements the topic model and allows you to easily create those time series. And furthermore, it also implements the RGC, which is an extension of the topic model. But I don't have the time to discuss it now. So I would say thanks to you. And yeah, well, it's over.
Great, thank you very much. And so we have come to the end of this talk session, and I would like to thank again all 4 of the presenters who have done a very, very good job, and they've all prepared to a very high standard. These are easily some of the best slides that I've seen for the entire conference. So well done to all of you. We have come to the end of our time, but I believe we can run slightly over. So if anyone has any burning questions, now is the time to ask. And if there are no other questions, then thank you for attending. And we have the final keynote coming up at the top of the next hour. So thank you all.
Thank you, Charlie.
Thank you. Thank you, everyone, for listening.
Thank you.